Welcome to Part 6 of the Mobiletuts Beginning iOS development series. This installment will cover Xcode debugging fundamentals. It will include a brief amount of software debugging theory and a practice application to demonstrate the use of breakpoints in the Xcode debugger. Instead of building a new application for this tutorial, I've taken the Fortune Crunch application that we created in Part 2 of this series, and I've introduced a number of different errors into the source code. Download Broken Crunch, the broken version of Fortune Crunch accompanying this post, to follow along as I demonstrate how to use the Xcode debugging tools. Before we begin actually debugging Broken Crunch, let's talk for a moment about software debugging theory. In general, software errors, also known as bugs, can be categorized as follows: compile time errors, runtime errors, and logical errors. As the name implies, a compile time error occurs when you attempt to compile your application source code. In Xcode, this happens when you select Build and Run or Build and Debug in order to launch your application on the device or simulator. When a compile time error is encountered, it will literally prevent your application from being launched. As we will see, errors in this category may either occur from nonsensical or incorrect syntax statements, or from problems that arise in the linking phase of your application build. Generally speaking, compile time errors are the easiest of the three categories to resolve because the compiler will typically issue a meaningful error message or warning that will alert you to the nature of the problem. Runtime errors occur after your application has been compiled and launched into the simulator or on a device. An application crash or memory leak that occurs as the result of poor object memory management is an example of a runtime error. A logical error occurs during the runtime phase of an application and results in unexpected or undesired application behavior that conflicts with the software developer's or project stakeholders' intended outcome. A good example of a logical error is a mathematical formula that has been implemented incorrectly. Consider the Pythagorean theorem: a squared plus b squared equals c squared. If a software developer unintentionally implemented this formula as a squared plus b equals c squared, the result would be a logical error. But it most likely would not cause the application to crash. That is what makes logical errors so hazardous. The application may seemingly run bug-free, while in fact producing invalid or undesirable output. With this theoretical knowledge in place, open Broken Crunch and let's get started. After loading our sample application, select Build, Build and Debug. You'll notice that the application fails to launch, and the compiler has generated a number of errors. To view the results of the attempted compilation, select Build, Build Results. Selecting the errors listed will take you directly to the line of code where the error is being reported. One important thing to keep in mind, however, is that the number of errors being reported by the compiler and the line numbers of those errors should be thought of as the best guess of what's wrong with your application, not a conclusive pronouncement. In fact, one simple syntax error can result in multiple errors being reported to the compiler that are seemingly unrelated to the problem. As an example, take a look at the expected bracket before setImage error line. If you examine the line in question, you should find that the syntax is perfect. As it turns out, the problem here isn't on the line reported, but the line just above it. Do you see the problem? The nslog statement wasn't terminated with a semicolon. This means that the compiler doesn't know that you intended to end the line after the last parentheses, and is viewing everything from nslog to the final closing bracket and semicolon after UI control state normal as one statement. Add the semicolon to complete the nslog statement. Save the source file and click Build and Debug again. Two of the three errors originally displayed should now be resolved. Next, select the No Declaration of Property error. As you can see, This error is reporting that the property we are attempting to synthesize doesn't exist. To verify this, open the Fortune Crunch viewcontroller.h file, where the property should have been declared. If you examine line 17, the syntax is correct, but we do have a mismatch between the property we have declared and the one we are attempting to synthesize. Objective-C is a case-sensitive language, meaning that the C in cookie must be capitalized to match the property we are attempting to synthesize. Update the property declaration in the header file to read. Save the source file and build and debug once again. This time, rather than opening the build results from Build, Build, and Debug, simply click the error icon in the bottom right corner of Xcode. One step forward, 4 steps back. The error regarding the synthesized property line is gone, but we have an entirely new list of errors. What happened? This is a good time to take notice of the different phases being shown in the build results window. Notice that we have one warning underneath the compile section of the build results output. This is the same section that our previous errors were being reported in. Now that the previous 3 errors have been resolved, we have been able to progress from the compile phase to the linking phase of our application build, and all of the new errors are linking errors. When you encounter a linking error, it's typically because you are trying to use functions from a framework that you haven't actually included in your application. In this case, the build results are referencing a function called UIApplicationMain in the main.o file. Main.o is the compiled machine code version of main.m. Let's take a look at the source code in that file. On line 13, you can see a function call to UIApplicationMain. UIApplicationMain is a central function to every iOS application, but how can you find out more about it and figure out what framework it is included within? Fortunately, the iOS SDK comes with some great documentation. If you hold down the Option or Alt button and double-click the function name, you will launch an abstract from the official iOS SDK documentation discussing this function. Click the book icon in the top right to view the full documentation available. You can see that doing so launched the function reference documentation for the UIKit framework. Bingo, we have our missing framework. However, before we add the framework to the project, let's examine another method that you could have used for determining the origin of UIApplicationMain. Close the documentation window. Now, hold down the command button and double-click the UIApplicationMain function. You are now looking at the source of UIApplication.h, the header declaration file that contains the UIApplicationMain function declaration. If you scroll to the top of the window, you will see that this file imports multiple other UIKit headers, and that the comment at the top includes the UIKit framework name. Let's move on to resolving these linking errors by including the UIKit framework. To do so, right-click or control-click on the Frameworks folder in the Groups and Files pane, and select Add Existing Frameworks. Find the UIKit framework and click Add. To test our work, select Build and Debug again. As you can see, the simulator launched successfully, and we were able to view our application. This means that we have resolved all of the compile time errors in our application. Go ahead and click the Fortune cookie. As you can see, clicking the cookie results in a runtime error, and the application has crashed. The message displayed in the bottom left of Xcode's screen isn't very helpful, so let's take a closer look by opening up the console. The console displays both a call stack of what was occurring in our program execution at the time of the crash, as well as a more detailed explanation. Terminating app due to uncaught exception. Fortune Crunch view controller cookie cruncher unrecognized selector sent to instance. This message means that our button is calling the wrong selector for the event that we fired by clicking the cookie. Since the interface for Fortune Crunch was built in Interface Builder, let's open the Interface Builder's zip file for Fortune Crunch view controller to take a closer look. Select the cookie button and control-click or right-click to view a list of connected actions. You can see that the touch-up inside event is referencing a target that doesn't exist, indicated by the yellow text. Remove the non-existent cookie cruncher target and reconnect touch-up inside to file's owner by selecting the crunch cookie target that appears in the dropdown. Save your work in Interface Builder, switch back to Xcode, and relaunch the application. Clicking the fortune cookie again results in a runtime error. This time, the console message isn't so helpful. It just displays EXC bad access. Take another look at the build results by selecting Build Results. Did you notice the warning earlier? Compiler warnings are often an indication of a potential runtime error, but because there is nothing incorrect with the actual syntax of the line the warning is issued for, the compiler is still able to build the application successfully. Of course, there are times when a compiler warning is a false flag and will not result in a runtime error, but upwards of 95% of the time, if the compiler has issued a warning, you're doing something wrong. Click on the warning to jump to the line in your source code where it occurred. The warning is referring to incompatible pointer types. The image named method expects an NSString object, but this line of code is supplying the method with a literal C-style string. Add in the @ to make this an Objective-C string. Save your progress and run the application again. This time, when you click the fortune cookie, you encounter a logical error. The application doesn't crash and the happy iPhone hacking label appears as expected, but the background image remains as the closed cookie. To fix this, let's take a look at the function responsible for the transition, IBAction crunch cookie. Line 19 is responsible for changing the background image, and you can see that it is setting the new background image to cookie-closed.png. If you take a look at cookie closed in the resources folder, you'll see that this is in fact the same image displayed when the app at first loads. We need to change that line to transition to cookie-crunched.png. Build and run the application again. And now, tapping the cookie results in the expected background image with the label displayed properly. Congratulations! You've just walked through the process of fixing compile time errors, runtime errors, and logical errors in an application. All the while, we have barely tapped into the powerful debugging tools available to you with Xcode. To continue our exploration of the more advanced debugging tools available, let's try to extend the Fortune Crunch app to make it a bit more interesting. Rather than displaying the static string happy iPhone hacking every time the cookie is crunched, let's build an array of multiple NSString values that could be displayed. Switch back to Xcode and open the Fortune Crunch viewcontroller.h file. Add the following data member: NSArray fortunes. This array will be used to hold our random fortune strings. Now, add the following method signature: generate random fortune. This line will declare a new method in our class that will be used to select a random fortune from our fortunes array. Next, switch to FortuneCrunchViewController.m. Since this class will be initiated from our zib file, we need to override the initWithCoder method and allocate the array we declared in the .h file, initializing it with some new fortunes. Now that we've created a new NS array, don't forget to release it in the deallock method. Let's move on to coding the generateRandomFortune function. These lines simply generate a new random index number that we will use to return to the corresponding fortune string. Finally, modify the crunch cookie method to use one of our random fortunes rather than the static text "Happy iPhone Hacking." Build and run the application after saving these changes. If you click the cookie, you will create a runtime error. To figure out why this is happening, we're going to use the Xcode debugger and custom breakpoints. A breakpoint is a flag that signals to your application that program execution should pause when the line within the breakpoint is reached. Running your application in build and debug mode allows you to use breakpoints. To set a breakpoint, simply click in the editor gutter on the line you would like to trigger a breakpoint. To figure out what's happening in our application, we're going to set our breakpoint on the NSLog line just after the crunch cookie method is called. Build and debug the application with this new breakpoint in place. After the application loads, click the cookie. If you look into the bottom left of Xcode, you'll see the status message "Stopped at breakpoint 1." This means the debugger has successfully stopped program execution at the breakpoint you set. You'll also notice that a red arrow indicates the current line of execution where the debugger has paused the program. So, what can you do with the debugger? More than can be covered in a single tutorial. However, there are 3 fundamental actions you can take at this point: step over, step into, and step out. All of these options are available to you from the Xcode debugger menu bar. If you press the step over button on the Xcode debugger menu, you'll notice that program execution continues to the next line. Step over will simply continue execution one line at a time within the current method, but it won't follow your code execution if it forks to another method. If you want to actually follow your code execution into other method calls in your code, you will need to use the step into button. As you can see, step into has actually taken us into the generateRandomFortune method, which is exactly what we want. Click step over again to see what happens when arc4random is called. Wouldn't it be nice if we knew what the chosen index variable has just been set to? Fortunately, we can. One of the best features of using the debugger is the ability to simply mouse over variables to quickly see their value. Clearly, the chosen index value is much larger than that of the length of our array. Unlike in some other programming languages, the randomization function we are using will return an integer, so there is no need to convert from a decimal to an integer by multiplying the value by 10. Update the line to read int chosen index equals arc4random mod 3. We're done making modifications to this function, so use the step out button to exit this subfunction and return to crunch cookie. Note that even though we didn't see it, the rest of the function executed as normal. Finally, take note of the activate, deactivate breakpoint button and the continue execution button on the Xcode debugger menu bar. Continue execution will simply allow program execution to continue as normal. You can think of it as the unpause button. Go ahead and press this now. Before we move on to turning off breakpoints, there is one more issue to tackle. What you have just experienced is called the Xcode debugger. It is very powerful, but there are also two other debugging modes available to you, the full debugger window and the mini debugger perspective. Let's build and debug our project again to take a look at these alternative perspectives. To access the full debugger window, click the debugging icon on the Xcode debugger menu bar. This window has significantly more information than the Xcode debugger. On the left, you have a stack trace displaying the context of program execution. To the right, you can see a quick display of the various variables currently held in memory. Selecting a different call stack signature will change your view in the debugger. You can change the debugger window layout by going to Run Debugger Display. Finally, the mini debugger is yet another debugging perspective available to you. I rarely use this perspective, but it is available to you from Run Mini Debugger. Since we just resolved the error introduced in our random fortune code, we no longer need the debugger to be on. Toggle off breakpoints. However, before we build the application again, let's adjust the font size of our fortune label. Open Interface Builder. Select the label and change the font in the inspector to Arial Black 9 point. Now select the Adjust to Fit box and change the minimum font size to 6 point. Now build and run your project again. Voila! Our application now functions as we intended. Now that you've been introduced to the basics of using the debugger in Xcode, consider applying the following guidelines in your everyday development workflow. Test in both the simulator and on a physical device. While the simulator is a helpful method of testing an application during the development phase of your product, it is not a replacement for testing on a physical device. This is because the simulator and an iOS device differ in important and fundamental ways. For example, the simulator is obviously running within the OS X operating system, and the file system on OS X is not case sensitive. However, the file system on iOS is case sensitive. So referring to the file cookiecrunched.png with crunch capitalized instead of cookiecrunched.png with crunch lowercase will work just fine in the simulator, but will actually fail on an iOS device. Another key consideration is that the simulator has much more memory available than an actual device, and this fact will often greatly impact the user experience. Finally, not all of the default applications that ship with iOS are available in the simulator, including the Maps and the App Store programs. This means that you won't be able to test code that generates driving directions with the Maps app or cross-promotes applications in the App Store while in the simulator. These are just a few of the differences that exist. I strongly recommend testing on as many physical iOS devices running as many different targeted versions of iOS as possible. Use the Clang Static Analyzer. The Clang Static Analyzer is a special C Objective-C static analysis tool that ships with Xcode. This tool is able to analyze your code for errors or inconsistencies that might otherwise go unnoticed. While the details of how the analyzer works are beyond the scope of this article, using it is fortunately very easy. To perform a static analysis of your code, simply select Build, Build and Analyze from the Xcode Build menu. If you would like to learn more about how the Build and Analyze option works, you can read about static code analysis on Wikipedia or about the Clang static analyzer from the official documentation online. Set a global breakpoint on Objective-C exception throw. In this tutorial, we learned about how breakpoints work by setting project-specific breakpoints in our code. In addition to project-specific breakpoints, Xcode will also allow you to set global breakpoints that will apply to all the iOS projects you create in Xcode. Setting a global breakpoint on Objective-C exception throw will allow you to automatically launch the debugger whenever an exception, which is a type of runtime error, occurs. To read more about the benefits of this approach and how to implement it in code, refer to my iOS quick tip on Objective-C exception throw and global breakpoints. Treat warnings as errors. As mentioned previously in this tutorial, the vast majority of compiler warnings that are issued should be resolved before you launch your project, and there should really never be a scenario when code that generates compiler warnings must remain unchanged in order for an application to function properly. Consequently, some programmers recommend treating all compiler warnings as errors, thus forcing them to be resolved as part of the normal development process. For all but a few fringe cases, I support this idea, and Xcode makes it easy to implement. Go to Project, Edit Project Settings, and then select the Build tab. Type Treat Warning into the search bar, and you'll see a Boolean value called Treat Warnings as Errors. Check this box to enable a feature. Build and validate before App Store submission. Another step you can take to increase the odds of your application being accepted the first time you submit it to iTunes is to enable the Build and Validate flag in the project build settings. Type Validate into the search box of the Project Settings Build tab, and then select Validate Build Product. This option will run some of the tests performed by the Apple reviewers, allowing you to potentially preempt an App Store rejection. It should be noted that checking this box is not a guarantee that your app will pass App Store review, but it is better than nothing. In addition to the console, build results, and the debugger, there are a few other great debugging and optimization tools that you should be aware of in your development efforts. For further reading, take a look at the official documentation for the following tools: Instruments, Shark, Top and Spin Control, and Big Top. This has been a whirlwind tour of debugging with the iOS SDK. There is still much more that can be done, but hopefully this lesson has been enough to help you more quickly resolve the bugs in your own applications and write better software. If you would like to hear more about some of the advanced tools discussed in this tutorial, such as Instruments and Shark or Spin Control, or if you would like to hear more about debugging in general, leave a comment below and let me know.